afternoon. I'm glad. So I have the chance to close this workshop anyway. Thank you for being here. So I would like to report some recent progress we made with Martin Franzel group, and in particular the work of Andreas Eggers. Should have been here to present because he deserved all the work. So, and also collaboration with Jakob. I guess most of you know. Okay. So the idea is to give you some insight about what you can do with this new reachability, nonlinear reachability piece of software that is in fact a layer around the vNode LP, which I guess most of you know. It's still, in my opinion, is the best state-of-the-art solver for nonlinear IGP-ODE. And combining this with the previous result of my own work, that is bracketing systems, and also ideas from the ISAT-ODE, which is a satisfiability solver for certain ODE equations. Okay. It would be nice to give you some motivations about why we have decided to make this piece of software available. So then, maybe at this time of the workshop, you are quite aware of the this kind of problems. Let's say hybrid complex systems, hybrid physical systems, these very complicated systems where you have interaction of discrete and continuous systems. Supervision, planning processes, and low-level controls and environments, continuous dynamics, and usually there are safety-critical embedded systems and networked autonomous systems as swarm robotics, for instance. And one particular problem for these kind of systems is verification. That is, we want to check that the system will behave normally, safely, for a given situation, and there is no, and sometimes it's very difficult to use analytical methods, hence we have to revert to numerical proofs, and either we can prove that it will always work, or try to find a false counterexample and classify assumptions. Okay. One way to do this, there are many ways to do it, but the one that is related to our interest is modeling using hybrid automaton. We have already went through this, and I will not focus mainly on this. Hybrid automaton is mainly a dynamical system for which the dynamics may evolve according to the location in state space. It can be a merely switched system, that is, there is no reinitialization of the state variables, or a hybrid system, that is, you can have resets for a hybrid system. When we do verification, there is a first step, that is modeling, and then within these formalism we have property specification, and then verification algorithms, and some of them, not all of them, some of them rely on reachability computation. So it's only a subclass of methods that are addressed here. So what we can do with nonlinear reachability or hybrid reachability, we can do many things. We can do verification that is given a subset of initial values. Let me just go first talk about continuous reachability first. Okay, given a set of initial values, these initial values can be state variables, but you can put their parameters, because you can plug the parameters in the state variable. You can put the controller tuning and so on. So this is quite general description of what is in searching, or what characterizes the system. So given an initial domain for state variable or initial conditions or parameter values, okay, the question is, can we compute the set reachable in finite time? And we have seen there are a couple of techniques, among which interval Taylor methods, and these keywords I will explain later. But let's assume up to now that we know how to compute this set reachable in finite time. So if we can do this, we can then hopefully solve the problem of the intersection of this reached set in finite time with the guard conditions that may lead the system to switch to another mode. Eventually it will switch, but it's not necessary anyway. And Musa has talked about a possible way to do this. There are many other ways, of course, but the way we are investigating currently we give you some clues about this idea. Okay, so if we know how to compute the set reachable over a hybrid state, or let's say solve the hybrid reachability set in forward time or in backward time, same computation, we would be able to detect whether the system can reach the forbidden area in finite time, and hence give a technical contribution to the problem of solving the verification issue. And if we combine forward hybrid reachability and backward hybrid reachability, we can come back to the initial conditions, the tuning parameters, and spot the ones that would lead to the forbidden area. And doing this, we can do reach avoid problems, such the one that has been investigated in traffic collision system or air traffic collision system, and one of the main contributors is Tommy and her colleagues, for instance, where she could, for these kind of situations, prove that collision is possible if we take into account all the uncertainties that may reside in initial conditions in the dynamical flow. Okay. We can also embed this hybrid reachability or nonlinear continuous reachability analysis in a bounded model checking framework, and we could embed this in a satisfiability solver, such ones that is investigated in Martin Franzel groups at Oldenburg, where they try to analyze the satisfiability of a satisfiability formula where transitions for the system can be described by ordinary differential equations. Okay, I just give you some very slight overview of this. The main idea is try to check whether the opposite of the property you want to analyze can be satisfiable when you unwind the system, the satisfiability formula. Let's say you assume the system will propagate in time, and you unwrap the system, and all transitions possible, and try to find one possible unwindings for which this property, the contrary of this property is satisfiable, and if so, then the property is violated. And if you can prove that there is no way this property is satisfied, hence you have